Okay, welcome to Cognos Education. Today we're going to be doing AP Physics 1, Unit 1, Lesson 1, the language of motion, which is scalars, vectors, and velocity. So first, we have a couple key definitions and facts. Scalar is a quantity, sorry, spelled that wrong, quantity that has magnitude, or which is basically size, but no, sorry, there's a comma here, but no specific direction. For example, we have distance. Um, Distance, it's just the length of the path you traveled. If you go 5 meters back, and let's say back is negative, you traveled, you still traveled 5 meters. It's not negative 5 meters. Speed. Even if you're traveling backwards where forwards is positive, your speed is still the same. Speed is how fast you were going. And then there's time. Time can't be negative. That's a fact. And then mass. You can't have negative mass. Okay, now we have the next thing, a vector. A quantity, and again, I spelled it wrong, that has both magnitude and direction. And direction plays a big role in physics. So for examples, we have displacement, which is your final position minus your initial position. So let's say your initial position is 5 meters, then you go 3 meters. Your displacement is -2 meters because you went 2 meters back. The distance you traveled is 2 meters, but your displacement is -2 meters. Then we have velocity, which velocity is the same thing as speed, but with direction. If you have negative velocity, you have speed in that negative direction. And then acceleration. Acceleration is the rate at which velocity changes. So since velocity can either be increasing or decreasing, this can be either negative or positive. And then lastly, we have force. We have negative forces. Something could be putting a force on something to the right, and another thing is to the left. If right is our positive force, then left is our negative force. And then we already talked about this, but distance, we have displacement is final position minus initial position, and distance is total length of path traveled. And then we talked about speed, and here, let me do another one. And this is just speed with direction. So now you go on to some core ideas. Um, Give me a minute, I'm sorry. Okay, so to add vectors, you basically, okay, to add vectors visually, you use the, let me write it out, tip to tail method. So for example, if we have vector A and then vector B, them added would be this vector C. So for example, if this is our resultant vector, by the way, it's basically the addition of these vectors. So positive, usually these vectors can be positive. Let me write that in. So for positive, which means up, right, forward. Most of the time it means this, but there could be questions where they mix this up, and they will tell you. And we have negative, which is left, down, backward. So we move on to some formulas. We have that average speed is equal to total distance, or just distance over, oh no, average speed, so total distance over total time. We have that average velocity, which is notated by this. That's velocity. That means that its average is equal to the displacement in x. So the displacement over the the change in x over the change in time. So the displacement over the change in time. So in more complicated terms, it's the final position minus the initial position divided by the fi final time. Oh, I meant to do a t. Final time minus initial time. And so now we have, oh, by the way, sometimes in mathematical derivations, we use y equals time. But really, when you start getting into more advanced physics, not even that advanced, you start to use t equals time. Well, really, you can use anything. It's just what you want and what you feel most comfortable with. So now we have our problems. So our first problem, a physicist walks 4 meters east, then turns around, walks 3 meters west. Oh my. The entire trip seconds. Find total distance and net displacement. So let's start visualizing this. We have our compass. We have our compass. North, never eat soggy waffles. So 3 meters west. So draw that as 3. Oh, so that is not a straight line. I'll draw it over here. So 3 meters west. Oh, well, first, I'm sorry. First, they walk 4 meters east. This way, and then they walk back 3 meters west. We can see this is forward to the right. This is back to the left. So since this is forward to the right and this is back, we would just minus these, and since this one's bigger, so this minus that. So we'd get our net displacement, which is signified as delta x, is equal to 1 meter east. But the total distance traveled is different. It's the sum of all. Sorry. Sorry, my headphones keep dying on me. Total distance is the sum of all the path lengths added up. So first we walk 3 meters. First we walked 4 meters, then we walked 3 meters. Those added up are 7. So our distance is 7. And our displacement is 1 meter, 1 meter east, which is right, 7 meters, my bad. Okay. Next problem. Using scenario 1, problem 1. Find average speed, average velocity during the 2-second trip. So we know that our total distance traveled was 7 meters and our displacement was 1 meter, or 1 meter east, but east is positive, so we can just leave it as 1 meter. And our time was 2 seconds, so we know average speed is distance over time, which is just 7 over 2, 3.5 meters per second. So our average speed, but our average velocity is different. It's displacement over time. Displacement over change in time. And our change in time was 0 to 2, so it's 2 minus 0, so 0. So that means that change in x is 1 divided by 2, which is equal to 0.5 meters per second. So you can see we get very different answers. This one has direction, east. This one is just in total, no direction, just pure magnitude, how much we traveled. This one accounts for direction. And problem 3. Okay, wrong color. A drone flies so delta x1 is equal to plus 12 meters, then flies backward. And our second change in x, sorry, that's a horrible 2, is negative 15 meters. And it's asking, is the drone's final position? Its starting point relative to. So we know we just add the vectors, which is 12 meters minus 15 meters, which is negative 3 meters, which gives us the total final position. Because we go 12 meters positively, and we go back 15 meters. So in total, we went back, or negatively, 3 meters. Okay, and lastly, we have a toy car starts at an initial and travels with a constant, which means it doesn't change. For average velocity, we'd be calculating usually for the average velocity, which is not the same as the instantaneous velocity, which is the velocity at any point. Because average velocity is finding the average of all of those, while instantaneous velocity is velocity at one point. But what this is saying is that the velocity is always constant, so it's always the same. No, my apologies. I'm not sure how I describe this, but constant average velocity, so the average velocity doesn't change over the time interval. So first, what we would do, let me go onto a blank canvas. So first, we would write down that average, let me do this in red. Average velocity is equal to the final position minus the initial position, because that's our definition for delta x, change in displacement, and then over the change in time. And our change in time is just 4 because we start from t equals 0, y equals 0. So we can just change this to 4, and then we times both sides by 4. These cancel out. So we get 4 times v equals x final minus x initial, and we can use algebra to add our initial position. So we get 4 times the average velocity plus the initial position equals the final position. And so evaluating this, we know that the average velocity is 3 meters per second positive, so we get 12, and it starts at initial position of -2, so -2 is equal to the final position, and this is 10 is equal to the final position. So plus 10 meters. That's our answer. Okay. Thank you for watching the video.